All right, thanks, Andrew, and everyone else is out there. So, yes, the topic of this is the hydrologic impacts of high-severity wildfire. And one of the reasons this is really important is that fires are often over and out in 2 weeks, but the impacts of this wildfires can go on for many, many years, and it's dependent on a whole bunch of factors we'll talk about. But so it's like, and we're going to discuss some of our experience in the Southwest. They've been seeing areas with more high fire severity, and the other thing is that with people moving into the forest landscape, there's more and more human resources that are at risk, and and so this is causing some counties real problems in states, and they're trying to deal with this, even cities that are at risk. In some cases, people don't even recognize the risk. So anyway, we're going to go through this. Let's see. And I'm going to refer to a bunch of stuff from the Schultz Fire of 2010 because this really highlights some of the impacts of these altered hydrology caused by high-severity fires. And although the Schultz Fire occurred on the San Francisco peaks, and it had a really high proportion of high severity, I think 60% of the burn area of about 15,000 acres was high severity. And it was a fire that burned in late June. I think 60% of the whole acreage also went up in the first day. So it's like, this was an eye-opener, but it impacted an area that with some significant amount of housing, and we'll show you some of that and what it did. And the thing is that the fire was over and done in 10 days, but the flooding is still going on. We're into the second year of it, and in many cases, in the past, you tend to get a fall off in these flood responses after about 3 to 5 years. But in some other cases, that's not so, and a lot of it's depending on what sort of precipitation you get. And I think you'll see from this that this fire resulted in a really major alteration of the hydrologic response of these watersheds. That ephemeral doesn't really flow, but now they do. So anyway, fire fits into a whole bunch of different ecosystem disturbances. Man causes. There's insects and disease, climate, geologic forces, and some of these come together in a synergism to create these big wildfires. And so you have fuel buildups, but also climate change. 2010 and 2011, we're often seeing fires that were outside the box in terms of their fire behavior, in terms of temperatures, wind speeds, relative humidities, and this hasn't been seen in the past. And all those things lead to these high-severity fires. Fire, of course, occurs across a continuum. If this is sort of a graph here to try to conceptualize that, is you've got fire severity going from high to low across the basin. You have a hydrologic event, and obviously, if you have a fire but you don't have a hydrologic event to follow it up, nothing's going to happen. It's when you get those hydrologic events. And there have been fires where first year after the fire, no big deal because the hydrology wasn't there. But the second year, some big storms came along and some stuff happened. And as you go, the upper end of this is sort of the yellow bar across the air is like probably below that level, whatever it is. There's not a whole lot happens. And then you start getting increasing stuff as you go on up towards the orange line. If you're in the upper corner there, where the circle is, then you get some real stupendous things happening in terms of the hydrology and then what it does to the landscape. So again, this is just sort of a conceptual way of looking at it. And we got to separate out wildfire and prescribed fire. Generally speaking, your prescribed fires aren't the problem, but sometimes they can get loose, and that's why you have that upper end there. And then with many ecosystems, it all depends on the event. I mean, if you get a really big storm event, sometimes you'll get a response irrespective of whether the area was burned or not burned. So that's why that RX fire curves up at the end. So the water and aquatic ecosystem impacts that we see after fires, they're really a function of the fire severity. If you get a fire that most of it's moderate to low, you're probably not going to get much of a response. We've seen some fires like that in the White Mountains in the past where high fire severity is less than 10%, and there wasn't really a whole lot of change. Also the watershed condition, and this keys back in severity and what it does to the forest floor and to the soils, and then the rainfall events. If you get the wrong event, follow the fire, then you're going to get some big hydrologic response. If that event doesn't occur, not so the case. Talking with some people from the Hayman fire, which was 2002, they're 10 years out and they're still getting flooding. And so when you talk to people that are shocked because they're being hit with these floods after the fires, well, they want to know when it's all going to be over. And it's very difficult to predict. There's this general rule of thumb of 3 to 5 years, but it doesn't always hold. In some cases, it may go on, and it could go on for decades. And it all depends on the system. And it's also, this is a worse situation in parts of the U.S. that have high-intensity summer thunderstorms. If you just got sort of gentle rain, during the summer, probably not going to get a big response. It's these high-intensity storms that dump a lot of water in a short time, as you'll see. Okay, some of the fire severity factors, the temperatures, affecting the heat and the fuels, if you get temperatures are up around 90, 100 degrees, that's going to cause a lot of severe effects. The rate of spread, how fast does the fire move, what area is being covered. If it's just little spots of high severity fire, probably not going to do a big thing. But if you get entire watersheds nuked off by high severity fire, then you're going to see something. And also the particular climate, the soils, how they respond. Slope and topography interact in there because that drives runoff events. And if you have very gentle sloping areas, you're not going to get some big responses. But if you have steep slopes, all bets are off, and you could see a lot of things happening. Just to look at, low severity fire. These shots happen to be from the Rodeo-Chedeschi fire of 2002. And this is in the Sturmer watersheds in the Apache Siggraves National Forest. And this area was actually burned. It was burned at low severity, went across, consumed some of the forest floor. Didn't really kill many trees. And after a while, you couldn't even tell it was burned except you had some blackened trees, the bases of it. Going up to moderate severity, all of a sudden you see is different. You have the fire was enough, let's see if I use this tool, to kill foliage. The foliage like that that's showing here is brown. In this case, was actually green right after the fire, but it was sort of flash fried by the fire. And you can see a lot of needles that are across the ground like this. They've fallen off. But anyway, and with moderate severity fire like this, you can have green patches here and there. You don't tend to get consumption of small twigs, etc. So this is a more moderate effect. You go to something like this. This is high severity. You have there's nothing up in the crowns because it's all but consumed by the fire. You have small twigs and branches are killed, but the important thing there is that, and this is during a rainfall event, is you see all the water is just ponding up. And normally in these soils that would have infiltrated, it's not doing that. It's ponding up and then running off. Let's see. Is that the end of part one? Maybe.
Yes.
Okay, so what causes that to occur is response to high severity fire. What do they do to the soils? Because first of all, they burn off the organic horizon. This is like a sponge that sits on the surface. It protects the soil. It absorbs water. Forested watersheds are, most of the cases known to produce high-quality water because of this sponge, because rainfall can't hit mineral soil, and it mostly soaks in. Okay, so you burn off that protective layer, the forest floor. It's going to affect hydrologic response. So you expose mineral soil, so the mineral soil particles are exposed to raindrops, and what they do. And also what fires do is create water repellency. There's natural water repellency that occurs in many sites, but this aggravates it. And the hotter the temperatures and longer duration, the greater degree of water repellency. So typically, like, fast-moving grass fire could have temperatures of 1,500 degrees Celsius. It moves through so fast it doesn't create much water repellency. But you get something that cranks along there, burns for quite a while, even at lower temperatures can create more water repellency. You can get some ash developing, and in some cases it's been reported that this is clogging the pores of soil, and this aggravates it. There's a lot of work still being done on that. But the net effect is it reduces infiltration and increases water runoff. And that water runoff is what causes the problems, both in terms of the water itself plus erosion. Water repellency. There's a shot here showing 2 drops of water sitting on a water-repellent soil. Normally, you expect water to hit the soil and infiltrate. Well, if you got water repellency, even where there's natural water repellency, it doesn't do it. It just beads up. And it beads up and beads up. And eventually, you get enough water there, it's going to run off. It's not going to infiltrate in the soil. And this is just a classical case. So this diagram here, you can see we have an area that's been burned, and there's a water repellent layer, which is developed along this black line there. That's the water repellent layer. So water comes into the soil, infiltrates for a while, hits that layer, and then moves laterally. And that can lead to erosion and a whole bunch of things. Now, the depth of that layer is dependent upon a number of factors related to the temperature of fire, duration, also type of material burning. In many cases, that water repellent layer is right at the surface, but in other cases, it can be deep. When I say deep, it's only 3, 4, 5, maybe 6, sometimes 10 centimeters deep, and that's it. Again, it's a function of the particular fire properties and the fire behavior. So sometimes if you after a fire you don't see any water repellency in the surface, that can lead you to a false sense of security that there is no water repellency. It may be deeper. And I saw some of this in the Cerro Grande fire where you had a big duff layer underneath a tree. When that burned, the water repellent layer was down about 4 or 5 centimeters, whereas out in between, when it was it was closer to the surface. Okay, and when we get that water repellency, and the rain comes along, everything's going to run off. And of course, this is what causes the big problems after fire is that rain, and what it does in terms of its effects downstream or the erosional effects. And this is a case of what it does when you start getting erosion. This is a shot from the Schultz Fire, fairly up high, and you can see a lot of rills and developing, and also small gullies starting to form. There's rills everywhere up in here across this whole landscape. There's all these rills. That wasn't there before. This occurred after the fire. After the fire, those slopes are fairly uniform and level. And but what you have is small areas that are not infiltrating water, and they feed into these gullies, adds more water, erosive power increases. Another factor dealing with this particular one, the Schultz Fire, is the steep slopes. In some cases, up to 100%. And the net effectiveness of this is it increases the hydrologic response of the watersheds, because you have increased the drainage network. And before, where water would have fallen on these soils and just infiltrated, now it's running off, and that leads to problems. And you can see this is a bigger shot, again, from the Schultz Fire. You notice all the streaking on the slopes going down there. It's just one after another. This is all rills and small gullies which developed after the fire. Again, that wasn't there before. So you have all of a sudden a whole slope like that, and this goes on for quite a distance of area that's now very responsive in terms of rainfall events. It's going to route water off real fast. And again, this was mainly caused by the first rainstorm, big rainstorm after the fire. You had water repellent soils, and no over-horizon, because all this area in here was high severity wildfire, and it just totally altered the hydrologic response of the landscape. It's quite astounding. Fire affects many different types of flows. It does affect the annual yields, the peak flows and the base flows. The peak flows are important because those are the ones that cause floods. Base flows, if you decrease, can cause some decreases in base flows, and the base flows are what provide the, where you have a perennial flow or sustained flow from forest watersheds. So if you look at annual water yield on all fires, we've got here fire type, RX, prescribed fire and wildfire, and the change and the duration. And you see for prescribed fires, you can have actually a decrease in water yield, or you can have a slight increase. And generally this occurs maybe in a scale of 2 to 11 years. Wildfires, you can get no change up to 3.5 times or more, and this may occur over a duration of 20 to 15 years. And they're getting more evidence on this. This can go off even further. So as these fires go on, they provide a fascinating laboratory to study them and understand them, their responses. If you look at flood peak flow response, this is the one. This is a real concern. To not only people that are managing wildlands, but also to city, county, state government officials, and federal. There's some locations. You see the state abbreviation, like here, North Carolina, and the loblolly is the type of forest, obviously, whether it's an RX or a wildfire. And there's a peak flow increase factor. Now, prescribed fire is loblolly pine, North Carolina, no change, because you don't have the high severity wildfire. And that was just put in here as just sort of a reference. Now, as you move to the wildfires, you start picking up higher severity. And Coon Creek Fire in Arizona in 2000 did that, 7-fold. And that was scary, because you had an area that had never really produced any real high peak flows. All of a sudden, jumped 7. But that's small compared. Look at some of these other numbers. Rodeo Chesapeake Fire did this, and it's just almost impossible to imagine. And that happened to occur on a smaller watershed. But even so, anything over 7, 10 times, 100, much less 100 times, is that often it's beyond our just range of experience, and we can't comprehend it. So we're again, this varies by region. It's going to vary again by how much the watershed is affected by high severity fire. In that, the one here with a 7-fold increase, that was off of a watershed that had a sub-watershed that had 100% high severity fire, and that dominated the whole flow. But anyway, and we were able to get some handle on that because we had some gauge watersheds in the area. Some cases you don't. In some cases just estimates. In the cases of both the 7 and the 2,300 times, there were gauges in place, but they're totally overtopped. So we have to go on estimates of what the flow was and the peak flow. And the thing about these flows off these fires is that water always wins, and it's very difficult to control this stuff. We'll talk a little bit about burned area emergency response later, but it's like if you have a landscape that's set up with high severity fire and you get the wrong rainstorm, you're really limited in what you can do. And the steeper the terrain you have, the worse it is. Some of the effects after fires, and this starts to give you an idea. High severity fire, and you can see some of the effects of different fires. The one on the right was up in Idaho. I don't remember the fire name, but this scoured off to about a level like that. And before it had a little tiny flow in it. This is the Hondo fire in New Mexico. You can see how the landscape dropped because one of these big flows came through, flood flows, and just carved this out. On the lower left, that's from the Schultz Fire, and there used to be a road about at that level. And this was scoured out by some of the first flows. I'll talk a bit about some of those later. But anyway, there's a pipeline you can see that was put in down this road. Okay, the road was created, the pipeline put in it. And it virtually sat for 90 years, and nothing big happened. All the drainages were sort of gradual swales. It didn't have this. None of this incision occurred. This all occurred after the Schultz Fire, and it's just, it's astounding what it did. So you have a complete alteration of the landscape. Now, these systems, like these gully systems like this, they're now been primed to be very efficient at routing water downslope. A couple of other shots. Again, this one on the right is from that one's from Idaho as well. You can see that the peak flood flow in there was up that line at the top, and you see the scour on the banks, down cutting. You know, normally the stream sort of runs along there at a very low flow, but that was the flood flow that came off. The one on the left is from the rattlesnake fire in the Chiricahua Mountains of Arizona, and you can see, for scale, there's a guy up there, and there's another guy down there, and that blew out in one storm. It was the particular landscape has got a lot of rhyolitic material, so it's very easily eroded, and you know, to see something like that, it's just amazing. But that just shows you the power of the water coming off these steep areas after severe wildfire. And where all that stuff go? This is Rucker Lake, Arizona. They say, what lake? Well, the lake sort of got buried because all this material that eroded off that previous steep cut and elsewhere went and filled the lake up. It's sort of funny because we were standing there scratching our heads about what to do with this, and this truck pulled up with a canoe on it, and two guys came trucking over there from Oregon. They wanted to know where Rucker Lake was, so they go canoeing. So we just pointed down, didn't say a thing, and they couldn't believe it. Anyway, the flood flows after these storms can move, after these floods can move a lot of sediment in a real hurry. Let's get back to the Schultz Fire. And the thing about the Schultz Fire is sort of a perfect storm in that you had this a lot of high severity fire. There was about 15,000 acres burned on the east side of the San Francisco Peaks, which you see here, and 60% or 70% of it was high severity. Some of the watersheds in there were close to 100%. There's a 3,000-foot drop between the tops here and these houses down here. And there was a lot of housing development there because it was a very pretty site looking at the San Francisco Peaks. But people were living on an alluvial fan that in the past has moved water, but in the very distant past. I think most people who lived out there didn't appreciate the risk they were in on it. Absent the fire, could have gone on for hundreds of years and nothing much happened. But they had this fire. And the San Francisco Peaks have had these big fires in the past. It's not totally unusual. But as far as most people who lived out there, never seen anything like this. and people even living in the Flagstaff area, which was settled around the 1880s. No, hadn't seen anything like this. So anyway, so you have this, all this urban area here that's at risk because of the flood flows after this high severity fire. Just to give you a shot of one of the flows coming off of the burned area, and this is down a place called Campbell Avenue. This is actually a road, and you can see there's water jumping up there. There are some. This was probably I'd classify as a bowling ball event, and I did that sort of jokingly. From the size of rocks, it was moving. But it's just a lot of water was coming down onto this road, and this was all coming off the fire. And the first flows that came off of that were really black and ugly because they were carrying a lot of ash. And this is at an intersection of the street. The street does something like that, and you can see the pretty violent water coming through. I've got a film clip, which I didn't include in here, that shows it in motion, and it's sort of a shock. And you're sitting there watching this stuff going, and you can hear big rocks bouncing along through this stuff. This sort of flow in there is it's hyper concentrated. There's two different flows that come off of these fires. This one is a flood flow, but it's hyper concentrated. About 40 to 50% of what you see there moving is sediment. It's not water. Further up the mountain, there were debris flows that are more sediment than water, and there was just like, big tongues of large rocks moving, and water was just a lubricant in it. It wasn't the main event. And further on down, even further, is you had a number of houses were flooded out. You can see this one here that got some water on it. Some of this was due to, it was an area that was flat. It obviously flooded in the past, a long distance past. Some of the reasons for the flooding was because there was no really functioning drainage network out here. You're out in a rural area. There's not a lot of regulations on what you do with the water, but also a lot of the houses were built at grade, so they had no spare room to be able to sustain something like this. So what sets these things off? What's the sort of inciting rainfall events? The worst ones occur with high-intensity thunderstorms. In the southwestern United States, we have monsoons that come in July, after we've had a spring fire season, and they tend to produce very short duration bursts of rainfall. And sometimes you can get 10 to 50 millimeters in 10 minutes, which is enormous. But it's not just the Southwest. There's other areas in the western United States that are prone to this as well. And then you get repeated storms on the eroded terrain. So the first storm comes along, slicks off a lot, creates this rill and gully network, and then the following storms come through, and they don't have to be as big, and they cause the same or bigger effects. Okay. Just to give you sort of what they do is that this is some data that Pete Robichaud developed, and it's from Montana. And what you see is the blue bars are rainfall amounts. The locations are on the left from different places, rain gauges. The green bars are what are the return periods of the storms. Precipitation frequency, going from 2 years up to 100-year events. But what's sort of astounding is that this over 100-year event was caused by only 15 millimeters of rain. However, it came down in 10 minutes. And that's the kicker, and that's what really surprised us. High intensity, short duration bursts. The Schultz Fire, looking at two storms from July 20th, which was the first big one that did a lot of the damage, and August 16th, that the rainfall return interval was only 10 to 25 years. But it produced varying amounts in these different basins here. But the sort of astounding thing was that the 10-minute peak intensity for basin 9 is 24 millimeters. That's a lot of water in 10 minutes. And August 16th produced a lot of erosional effect, and it was a second debris flow producing storm, but it didn't have as much rainfall. Basin 9, which had 43 millimeters during that storm, we only had 27. And the peak intensity was 15 millimeters, not 24. But sort of caveat in all these are underestimates of the July 20th event particularly, because the rain gauge network at the time was down fairly low compared to a lot of the energy from these rainfall events occurs up at the high altitudes where slopes are steep, and so we didn't have any data on that. So the rainfall was, depending on which gauge you had, was somewhere between a 10 and 25-year storm event. This is based on Weather Service data from Flagstaff. It goes back quite a while, to the turn of the 20th century. But actually, the shocker was the flow was probably 1,000 years plus. And the reason we say that is that there's some geomorphic evidence that flows of this size have not occurred in 1,000 years. There was a volcano called Sunset Crater which erupted 1050 to 1100 AD, somewhere in there, that put a layer of this coarse scoria at the surface. And so the upper layer of the soil out there was this coarse scoria. Then you had some litter in there. After this July 20th flow event, there was about 10 centimeters of fine ash and soil. So that a deposit like that had not occurred since that previous eruption. So we don't know how far back it goes beyond that. Obviously, this area, we certainly didn't have rain gauges in there, and I doubt if the Indians made any comments about it. But that's sort of the scale. You had a 10 to 25 year rainfall event, and this high severity fire occurring in this area. You got a flood flow that's 1,000 years or more. Some of the other things related to hydrologic effects of severe wildfires. Some of it relates to suppression, water quality effects of fire retardants. There's been a new analysis by the Forest Service on just exactly what those are. And the fire retardants are ammonium phosphate based. They're essentially fertilizers. Problem is they're toxic to fish and other aquatic invertebrates. So a lot of care is required in how those are placed. There are water temperature effects, another part of water quality, and it's a function of how much of the watershed is exposed, particularly along the stream sides and riparian areas. And if you're dealing with cold water fisheries, this is real important because they're very sensitive to temperature changes. Warm water fisheries, not as you see in the Southwest, not so much the case. After the fact mitigation, what can you do? Not really anything. Some data from, actually this is from Washington, from Wenatchee area, after the Entiat fire. And you can see the temperature increase. This is over an interval of 8-10 days. And what you would have seen before the fire is down here in blue. And after the fire, you can see the temperature increase. And so you have anywhere from 2 to 6 degrees. And depending on what the requirements in the particular organism, it could have some serious effects. But anyway, so this is very common, is you get these temperature increases after fires. Another one is the big thing is fires and fish. And there's little or no immediate post-fire fish mortality. Fires don't kill fish. What does is stuff that happens afterwards, these flood flows. And this is sort of a comparison. Yellowstone fire, what was that, 88. Their fish were studied pre and post-fire. Populations were high across the entire time. Dude Fire, which was in Arizona in 1990, fish populations were high pre-fire. 1 week after the fire, it's still high. 2 weeks after, zero. What happened? Well, you had one of these flood events occur due to a monsoon storm, and it just flushed a lot lot of ash and other stuff into the streams and just blew the fish population out. So there again, fires don't kill fish, it's the flood flows afterwards. And I guess a few special topics I just hit on, and this picture shows one of these ash flows. Where are we? Yeah, this captures it pretty well. It's actually pitch black. It's ash and fine soil coming off of the Schultz Fire. That's the stuff that kills fish and aquatic invertebrates. It's a combination of toxic effects plus physical effects on their gill systems. Okay, I gotta go to number 4. Another topic is related to woody debris and water quality, and you can see on this picture here, this water flowing through there is actually jet black. But the thing is that the concern is on some of these debris dams can sometimes build up, and there's been a lot of controversy on whether they should be pulled out of streamside areas or just left. But sometimes you can get during a storm event, this debris piles up, creates a damming effect, and then it breaks, as it did here. As you can see, the right-hand side of it's gone. That can cause a higher peak flow, and that's a concern for that. Burn area emergency response, that's a whole separate topic. Could go on for quite a while on that. But the objectives of BEAR is to try to mitigate some of the immediate post-fire impacts, protect resources. The general public probably thinks it's going to stabilize and rebuild the watersheds so nothing bad can happen, but that's not necessarily the case. There's a whole variety of different techniques that are being used. It's expensive, but it can't save you from everything. Aquatic ecology is another thing, because often these stream systems subjected to these flood flows have really been altered in terms of not only their physical structure, but also their water quality and other things. And then you can have areas that provide a lot of habitat can get jammed up with sediment, and that affects the aquatic ecology. Again, that's another whole topic. So in summary, we've gone through and looked at the hydrologic effects of that occur after these high severity wildfires, and this is something that can put human populations at risk and adversely affect fish and other resources. It's something that can go on for quite a while as well, and a lot of that depends on how much high severity fire you have, what sort of landscape you have, what type of precipitation events you get. And people after the Schultz Fire coming up to us, they wanted to know when this is all going to be over and done with. And really all we could say is that some of our understanding from history and some other fires, that generally these watersheds will tend to heal themselves over a 3 to 5 year period, but that's not always the case. I'm sure they'd like to know it was all over and done right now, because the fire was over and gone in 10 days, but then now they're into the second year dealing with these floods. And we've been through disasters before that it's really bad, where you have it's one thing where the disaster is a one-time event and then that's it, but where it recurs and occurs again, it can take a real toll on humans, and also it's really affected things like land values, house values, and a whole bunch of other things. But it's important to understand that these sort of things can occur after fires. We're trying to get some funding to make some wider scale assessments across the western United States and try to identify areas that are at risk for some of these things like the Schultz Fire occurring. But anyway, and you should always remember that water always wins. You can do some limited things to stop it, but if you get too much water, you're not going to control it. And unfortunately, in some cases, it's had some really nasty effects. This is a flood flow after the Schultz Fire going right by a gas station. And with that, that's the end. I've talked for, I don't know.
Well,
40
Dan, thanks so much. That's a great presentation. And there are a couple of comments and questions in the chat box, some of which I think you've addressed. You can read those as well. One came in from Cheryl Mulder about one of your slides early on about the measurements of peak flows and whether they were modeled or measured. And my understanding from your talk was that in many cases they were gauged watersheds, but you had to estimate because they went over the gauges.
Right. They were measured. They didn't stay inside the confines of the gauge, and so you have to then go back and use some other indirect techniques to determine the flow. And it's just generally by the height of the water, the slope of the drainage, and then you run through some models. So it wasn't totally modeled in that, but models were used to estimate what the flow was. Yeah, it's sort of humbling when you have a gauge in there and the flow comes along and it's way over the top of it. But most of those figures from 7 on up were estimates because gauges were overtopped.
Okay. Linda Wadley was asking about some of the background materials supporting the fire history in the San Francisco peaks. Yeah, well, there's areas of aspen up on the peaks that probably were old fire scars. On the east side, we just know that this has occurred in the past because you have this erosional landscape there that probably, the alluvial fan was deposited by these events that occurred periodically. Not in short human time, but they've occurred over thousands of years. So we know that there's been a lot of water coming off those peaks to move that amount of material. That's the evidence that this has occurred in the past. And Lori Peltz-Lewis had a question about the K-rails function. And I'm not sure, maybe I'm going to go ahead and unmute the line so Lori can sort of clarify her question. So everyone, we have some hold music. Maybe somebody could turn off that hold music and I'll try unmuting everyone again. Yeah, Lori, the K-rails Schultz Fire to try to protect some of the houses up in that area. In some cases, a K-rail is also called a Jersey barrier. It's just a big, long concrete, that's a barrier. You drive down a highway and they're doing highway construction. They put up all these concrete things. Those are K-rails, or Jersey barriers. And in some cases, they held up pretty well, particularly where they were set up so that flood flows didn't hit them directly. There were some other spots where I saw K-rails rolled over by flood flows. Another spot along Campbell Avenue that's showing the upper end of that last slide there. There were K-rails, and flood flow came along, and when it was all over, the K-rails were buried in the channel bottom. They just got undercut, and water moved them. So, but there's lots of good examples of proper placement around houses. It helped. Does that answer that, Lori? I think I've put everyone back on mute because it sounds like we've got some hold music going, so we'll just stick with the chat window, I think. But there were some other questions. Robert Taylor put in a question. Since the consequences are so bad, is there part of the discussion on how to reduce the risk of high-severity fires? And I think many folks on this call spend a lot of their time worrying about that question, but maybe, unless, Dan, you want to comment on it, it seems largely a separate topic. Yeah, it's a separate topic, but also if you don't want to have these sort of events, you try to reduce the severity. And this burned through an area that had not been thinned in modern times, and it was really heavily stocked. Where the fire started was an area that was supposed to have been thinned, but wasn't. If you get in the wrong sort of terrain, I mean, some of these high mountain peaks, they're not ever going to be treated or whatever. And if you have a high density, you can get this sort of effect. I mean, parts of Mount Lemmon down around Tucson that you had some similar sort of flows occurred off of there. Well, and it's expensive to do that. In some cases, you're limited by terrain and what you can do. I think the important thing is to get people to recognize the risk. Living right next to this, nice beautiful mountain, whatever, it can be fine, but the mountain's not necessarily benign. And you get the combination of the perfect storm of a high severity wildfire and then flood flow events. This is what can happen.
Ann Bradley put a question in about how long woody debris flows continue. You talked a little bit about sediment coming down 3 to 5 years after and maybe much longer, but what about the woody debris component?
Well, it sort of comes down two phases. I mean, the initial storms can move a lot of stuff that's on the fire, but then as you go on and you get a lot of fire-killed trees dropping down, it can pick up. You can have an increase of woody debris, but generally there's an initial pulse of woody material coming during maybe a 5 to 10 year period after the fire, and then it drops back to probably below normal or back to normal. But yeah, it's it does occur, and if you get enough of these flows to kick some of this woody stuff out of the stream channels, well, and then it's going to drop off. Generally, it's some of the earlier flows that are the problems. But
and
anyway.
Laura Peltz Lewis had another question about whether there will be a report sort of summarizing some of this information about the Schultz Fire, or so are you putting anything hard copy together, Dan?
Oh yeah, there's two things already in the Schultz Fire. Well, there was a set of papers that was it was in the the Arizona Hydrologic Society had a meeting in September, and there's some papers in that and their proceedings. There's also proceedings of an international conference in Portugal on the fire effects on soil properties. It's FESP3. We had 4 papers on it that summarize a lot of this. There are 2 papers that will be coming out in Geoderma before too long that look at the rill and gully formation aspect, and the other one looks at the comparison of some of the bare treatments, namely rock riprapping at high altitude, culvert removal at lower altitude, and then use of rock wire gabions. I could have gone into, I have a PowerPoint that just deals with that topic. I didn't get into it, but some of the bare treatments are real effective. The culvert pulling was great. The mulched area, that worked pretty well where they could mulch. There was some surprising stuff like at the upper elevation on the San Francisco peaks, where there's a waterline road. There was a bunch of rock armoring. I mean, we're talking about big rocks. I mean, they're 2 and 3 foot in diameter. We're up there to armor the channel area. July 20th storm took them all out. They're just gone. You'd have to look hard to find that there was anything there. Culverts in the urban area that weren't pulled were very frequently buried and choked up. And like there's even some big box culverts that were put on this Campbell Avenue area often get buried in individual storms. And there's something like they're 8-10 feet wide and 6 feet high. Anyway, so if you want to send me an email, I can tell you where the URLs for those. I think they're on our website, but yeah.
Dan, I'll work with you, and when I send out a follow-up email, I'll send out a link to the recording of this webinar, and we can also put in some links to these URLs so that the people can track them down. And Sharon had a question about total organic carbon and bare treatments. The rodeo Cheddar Sky produced a bigger pulse and longer lasting source of total organic carbon than the wallow, which poses a treatment cost for downstream water systems. How much can bare treatments be credited for decreasing total organic carbon from wallow, or how much was luck? What do you think, Dan?
I think it was luck. There was a lot of bare treatments that were done, mulching to stabilize slopes. That probably had some effect because applying mulch is pretty effective. One of the differences between rodeo Cheddar Sky and wallow is that the high severity fire areas within the wallow fire were sort of spaced out. They were you didn't have huge areas of high severity fire. The rodeo Cheddar Sky, the watersheds that contributed to the organic flux, and the fact that there was a lot of organic material put into Lake Roosevelt that just blew away their water quality for a while. It came off some 60 to 80,000 acre watersheds on the White Mountain Fort Apache Reservation that were just nuked. I mean, it's like, if you went and looked at it, you'd swear an atomic bomb went off. And it was those watersheds that produced a lot of that. And there's a lot of steep terrain, just on the edge of the Mogollon Rim there that produced that stuff. And there again is a terrain effect. There are parts of the wallow fire where you have steep terrain, but there's also parts of the wallow where it's not as steep. And so I think it was just that it was spread out. I hope that answers it.
Are there other questions? You can go ahead and type them in here. Robert Taylor just put a question in about collecting data on the cities and counties and the money spent on cleanup. And obviously that could be used as future justification for education, if not treatment.
Oh, yeah. Well, yeah, I've got a rough handle on what they've been spending. Like Coconino County, I think, has already overspent over $4 million. They're getting a $6 million grant from NRCS to put some drainage ways to handle the water coming off the fire. And I think the city of Flagstaff is spending $6 million to repair the waterline road. The waterline road carries this water line, which provides about 20% of Flagstaff's water. Yeah, so we got a handle on that. Some of the effects on the urban areas would have been mitigated if there had been a drainage system put in place before this area was ever developed, but it was sort of wildcat development, and there was no planning. And of course, probably a lot of people would have grabbed their guns and gone up in arms if you just suggested doing that before. But I think a lot of it's also, education is important so people understand the landscape they are in. So yeah, the cost is high and it still keeps running. I think, ultimately they will spend a lot more on the bare and dealing with the flooding than cost to suppress the fire. I see there was a comment here on and of course this is a whole other issue of how do you deal with these flood flows coming off, because there are people saying, well, stop on the Forest Service land, and there's limitations on doing that. In Southern California, in some places they have these big debris basins at the bases of some of their streams because the hills around Los Angeles burn frequently and they produce a lot of sediment. But then they have to have money to come out and clean those basins out. And there are flood control districts in California that provide the funding to do that. And that's another big question here is that, okay, if you need to do something in terms of maintenance over a long period of time, who's going to pay for it? Where's the money going to come from? and then there's limitations of what you can do. One of our local politicians wanted the forest to route the water around the timberline area, and that has big limitations because of the high sediment load of these floods. Because anytime you change the grade of a slope, sediment drops out, and so what you're dealing with there is an alluvial fan that's not been active for a long time. All of a sudden became active. There's some other areas in the state of Arizona or in the west where these fans are more active. And it's obviously the risk. You can see the risk. But where you have something which has never occurred in the history of an area or a person's lifetime, you often don't see the risk.
Well, maybe that's a good note to wrap up. I think your presentation did a great job of illustrating the risk and providing some real hard data for it. So, Dan, I'd like to thank you again. You did a great job, and this, as I mentioned, we'll send out an email with a recording for this webinar so you can share it with your colleagues or watch it again if there was a part you missed, and we'll include in that email some links to some of Dan and his colleagues' publications on the topic. So thank you for participating, and I'm going to close off the webinar now, so it'll kind of kick you out, and we'll shut down the phone line because it's just about 1 o'clock here. So thanks again, Dan.
Okay. Glad to, thank you for the invitation, and glad to do it.
Great.
All right, bye.
Bye.